أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. In today's lecture we will be talking about entropy and third law of thermodynamics. This topic has been taken from the course outline of thermodynamics, having the course code of PHY331. Basically entropy, we can discuss entropy from the reversible and irreversible processes. Reversible processes are a type of ideal process where a system can come back to its initial state without losing any sort of energy, where in all natural processes are irreversible processes. If we consider a reversible engine, then there should be the following relationship between the heat transfer between the heat reservoirs at different temperatures. The QC divided by QH should be equal to TC divided by TH. So if we do the cross multiplication and write the same equation, then it will be like QC divided by TC, it should be equal to QH divided by TH. Here this quantity Q divided by T is same for both reservoirs. So this is conserved quantity and this is defined as the change in entropy. So how we can write the definition of entropy? This is actually the change in entropy del S is equal to Q divided by T, and this is expressed in the unit of joule per Kelvin. Like internal energy, entropy is a state function, so unlike energy, entropy is not conserved. If we consider a reversible processes or a reversible heat engine, the entropy of the system remain constant. So how we can express the entropy of a system if the efficiency of the engine is lower than 100%? So if we consider a real engine whose efficiency is lower than 100%, that is not actually a reversible engine. So in this case there will be less work part of the energy will be wasted to complete the cycle, and the equation for that particular case will be 1 minus QC divided by QH should be less than the 1 minus TC divided by TH. Or furthermore, we can write the same equation like QC divided by TC should be greater than QH divided by TH. So the total entropy of the system should be written as del S as a change in entropy of total should be equal to minus QH divided by TH plus QC divided by TC. It should be greater than 0 for irreversible processes. So any irreversible processes results in an increase of entropy of the particular systems. So just like we have very simple example of one irreversible engine who is operating between the temperature of 550K and 300K, that is extracting 1200 joule of heat from the hot reservoir and produce 450 joule of work. So how much entropy will be created in this process? So del ST should be equal to QC divided by TC minus QH divided by TH. So if we put the values in this equation, the del S total, the total change in entropy should be plus 0.318 joule per Kelvin. So how we can generalize the concept of entropy or the idea of entropy in this case? The total entropy of the universe increases when there are irreversible processes. If we consider irreversible processes, then the total entropy of the universe increases. When we consider irreversible processes, then the entropy of the system increases. But if we consider the normal reversible processes, the entropy of the system remain constant. As in universe, there are all irreversible processes. So therefore, we are moving toward the increased rate of entropy. So since all processes are irreversible, the entropy of the universe continuously increases. So if entropy decreases in a system due to work being done on it, a greater increase in entropy occurs outside the system. So it means generally that if there is in some place decrease in entropy, this could be done at the cost of very increase in entropy of that surrounding. So we have a simple example here of the order, disorder and entropy of any particular systems. So entropy can be thought of as the increase in disorder in the universe. So here in this diagram it is clarified that the end state is less order than the initial state. So the separation between the low and high temperature area has been lost. Here it is clarified this is the low temperature case and this is the high temperature case, and how the heat transfer between the two to achieve the same temperature. So here we have intermediate temperature between the two. So the entropy, generally if we have general recommendation regarding the entropy, then the total entropy of the universe increases and its ability to do work decreases. This means that we are losing useful form of energy. So the excess heat exhausted during an irreversible process cannot be recovered into a more organized form of energy or temperature. That energy which is exhausted or that is wasted in any particular irreversible processes, that could not be utilized anymore. So we are losing that form of energy. So doing that would require a net decrease in entropy, which is not possible. So if we relate the entropy to the second law of thermodynamics, then it will be like the definition of entropy with respect to the second law of thermodynamics. Our general description will be del S is equal to Q divided by T. So another statement of the second law of thermodynamics that the total entropy of the isolated system never decreases. So this is also another description of the second law of thermodynamics, that if we consider an isolated systems, then it is impossible that the entropy of that particular system should decrease. It may increase or it may remain constant if there is irreversible processes. So how we can manage the order to disorder of any particular system, that is actually increase in entropy. So entropy is actually the measure of the disorder of a system. So this gives yet another statement of the second law, that is the natural yes. So all natural processes tend to move towards a state of greater disorder. Just like we have a simple example, putting milk and sugar in coffee and stirring it, you can wind up with coffee that is uniformly milky and sweet. No amount of stirring will get the milk and sugar to come back out of the solution. So here we have another order and disorder of any particular systems. That is another example. When tornado hits a building, there is a major damage. So you never see a tornado approach a pile of rubber and leave a building behind when it passes. So thermal equilibrium is a similar process. The uniform final state has more disorder than the separate temperature in the initial state. So there is a growth of an individual and evolution of species. Or growth of an individual and evolution of species are both processes of increasing order. Do they violate the second law of thermodynamics? The answer is no. These processes are not actually performed in the isolated systems. Energy comes into them in the form of food, sunlight and air, and energy also leaves them. So the second law of thermodynamics is the one that defines the arrows of time. Processes will occur that are not reversible, and movies that run back will look silly. So unavailability of energy is also the consequences of the entropy. So and also the consequences of the second law of thermodynamics. The unavailability of energy is also called as a heat death. So if we consider any natural processes, some energy becomes unavailable due to useful work. As we are looking toward the toward the cycle of the second law of thermodynamics, it is impossible to complete the cycle of any particular engine without losing or without wasting part of energy. So that part of energy is unavailable, or that become unuseful to us, and that is not used as a useful form of energy. So we are losing that energy, and that is why that lead to the heat death. So if we look at the universe as a whole, it seems inevitable that as more and more energy is converted to unavailable form, the ability to do work anywhere will gradually vanish. So this is called as the heat death of the universe. So a macro state of a system is simply specified by giving its microscopic properties, that is temperature, pressure, and some other properties. So microstate of a system describe the position and velocity of every particle possible. So for every macrostate there are one or more microstates are possible. So here we have a very simple example to describe the concept of microstate and macrostate, that is actually the part of statistical mechanics. So tossing 4 coins, the microstates describe how many heads and how many tails there are. The microstates list the different ways of achieving that macrostate. So here in this case we have 4 microstates with all the heads, we have all heads, so 1 microstate is possible. So if we consider macrostates, there are when 3 heads and 1 tail, so 4 microstates of such types are possible, and 4 such type of arrangement are possible. So if we have 2 heads and 2 tails, so 6 such type of arrangements are possible, and it means that 6 microstates are possible. And in case of 1 head and 3 tails, 4 such type of arrangements are possible, and at the end for 4 tails only single arrangement is possible. So when we assume that each microstate is equally probable, then the probability of each microstate then depends on how many microstates are there. I mean, the most important example is that normally according to the postulate of probability, all microstates of any particular process are equally probable. But the question arises that if there are many microstates, then the probability will reduce. So the number of microstates quickly become very large if we have 100 coins instead of 4. So the table on the next slide, in the next slide we will list some microstates when we have 100 coins, and it also shows the microstate, the relative probability of each particular systems. So note that the probability of getting fewer than 20 heads or tails is extremely small. So this is the table describing 100 coins in their arrangement. Moreover, the number of possible microstates and the corresponding probability is also provided. So if we have 100 coins, then all 100 coins carry the heads and no tails is a single such type of microstate is possible, and the probability for this particular microstate is 7.9 multiplied by 10 to the power minus 31. So if we have 99 heads and 1 tail, so the corresponding microstates is 1.0 multiplied by 10 to the power 2, and the corresponding probability is 7.9 multiplied by 10 to the power minus 29. So similarly, moving toward the higher head and lower heads and higher tails, we can arrange such type of possible arrangement. And finally, when we have 10 head and 90 tails, so the corresponding probability will be of each one. The possible number of microstate in this case is 1.7 multiplied by 10 to the power 13, and the corresponding probability is 1.4 multiplied by 10 to the power minus 7. So at the end, if we have all tails and no head, so single microstate is possible in this case, and the probability of this single microstate is 7.9 multiplied by 10 to the power minus 31. So this is a simple arrangement of the different. If we are increasing the number of particles, definitely the number of microstate will also increases, and that will influence or change the probability of that particular systems. So this is a simple table describing the number of microstates and the probability of 100 coins. So if we interpret the entropy based on statistical mechanics, then we can say that the second law does not forbid certain processes. All microstates are equally probable. However, some of them have an extraordinarily low probability of occurring, just like we have a lake freezing on a hot summer days. So we have our broken clock reassembling itself all the year, or maybe some other example that all the year in a room moving into a single corner. So we generally know that how some probability just got just in going from 4 coins to 100. If we are dealing with many moles of material, then they can become so rare as to effectively impossible. So this is the simple example or description regarding the thermal pollution or the global warming, and due to the increase in entropy, and that leads to the energy death. So that is why we are losing toward the useful form of energy, and we are losing and we are searching for renewable sources of energy. So the generation of electricity often involves a form of heat engine, whether it is powered by biomass or solar power. Cooling towers are also features of many power plants. So here we have a simple example of a heat engine where it is moving and it is creating energy. So that is the source of water moves the turbine, and or maybe this steam is also used to move the turbine, or in some case we have windmill where the wind is also used to move the turbine. So what happen as a result of the motion of the turbine, there is electric generator, and this electric generator generate electrical energy that is further and that is created and moved. So the heat output of any heat engine QL is referred as a thermal pollution, and it must be absorbed by the environment. So air pollution is emitted by power plants, industries and consumers. In addition, most forms of combustion results in a buildup of CO2 carbon dioxide in the atmosphere, so contributing to global warming. Though this can be minimized through careful choices of fuels and processes, the thermal pollution, however, is a consequence of the second law of thermodynamics and is unavoidable. It can be reduced only by reducing the amount of energy what we are using. So here we are moving toward the third law of thermodynamics. How we can express the third law of thermodynamics, that says that it is impossible to reach a temperature of absolute zero on the Kelvin scale, or T is equal to 0 is often referred as a absolute zero. So in other words, another statement of the same third law of thermodynamics is that the entropy of a true equilibrium state of a system at T is equal to 0 Kelvin is 0. So strictly speaking, this is true only if the quantum mechanical constant is non-degenerate. If it is degenerate, so what happen? Entropy at T is equal to 0K is a small constant, not 0. So this is equivalent and to that it is impossible to reduce the temperature of a system to T is equal to 0 Kelvin using a finite number of processes. So the third law of thermodynamics describe the absolute zero, and it says that absolute zero is a temperature that an object can get arbitrarily close to but never attain. So temperature as low as 2.0 multiplied by 10 to the minus 8 K have been achieved in the laboratory, but absolute zero will remain ever elusive. So there is just simply nowhere to put that last bit of energy. So this is actually called as the third law of thermodynamics, that states that it is impossible to lower the temperature of an object to absolute zero in a finite number of steps. And if we summarize all these three processes in a single slide, the first law, second law, and third law, then it is like that the first law says that a continuous system cannot output more work than it takes in heat energy, and the second law says that the efficiency of heat engines should always be less than 100%, and finally the third law of thermodynamics says that Tc is equal to 0 is not achievable. So this is something about the entropy, third law of thermodynamics, and the statistical interpretation of entropy. So this is something of today's lecture. Thank you very much.